So the current unit is called dynamics, but deals with Newton's laws. Newton's laws deal with primarily the relationship between force or forces and acceleration. What is a force? It is a push or a pull, very simply. A push or a pull. Aristotle asked, what is the natural state of motion for an object? And his resolution was that an object tends to stay at rest and be at rest and end up at rest. Its natural state of motion is to be at rest. And he took this from his observation that as things were pushed and pulled, if you released them, they eventually went to rest. Of course, Galileo had a different idea. He had a way to experiment and test and show that possibly something else might be the case. He had a metal marble on 2-wire tracks, and he made them into a U-shaped track, and he released the marble and found that it came pretty much back to the same height. He thought, what would happen if we made the track a bigger, longer U, starting from the same height? And he let the marble go and found that indeed it went back to the same height as it had started from. And he tried it again with an even longer U-shaped wire track for the marble and found again that it came back up to the same height. So then his question was, well, what would happen if we never brought it back to the same height? And according to his, of course, he didn't make an infinitely long track or anything, but he showed that the object, once it's in motion, tends to stay in motion. And this is contrary to what Aristotle thought. So the natural states of objects are either at rest or in motion, which would be a constant velocity either of 0 or some other number in a fixed direction. So Newton's first law comes from Galileo's reasonings, probably even his writings and his experiments. And it says an object will not be changed from its state of motion unless the forces acting upon it are unbalanced. So it will not be changed from its state of rest unless all the forces after cancellation leave something left over in one direction, or if it's already in motion, it will not be slowed or sped up or changed, have its direction changed unless the forces acting upon it cancel out to leave something left over in one direction, some force left over acting upon the object in one direction. Another restatement of Newton's first law is an object at rest will stay at rest unless acted upon by a non-zero net force. Now, net force is a force what's left over after cancellation. For instance, just like your net paycheck, your net pay is your gross pay with cancellation from taxes and fringe benefits. So after you cancel out some of your gross pay, what's left over is the net pay. Same thing with net force. If you have forces in one direction and forces in another direction, things that are in opposite directions can cancel each other. If after you've put all the forces together, made a vector sum of them, if something is left uncancelled, so you have a non-zero net force, then the object will not stay at rest. But it will stay at rest unless there is some leftover force after cancellation. Also, it will stay in motion in the same direction. That means have a constant velocity, no acceleration, unless it's acted upon by a non-zero net force. That means a force that after cancellation is left over in one direction. Here's a more positive way to state it. An object will only accelerate if there is a net or unbalanced force acting upon it. So it will only have a change in its velocity if the forces acting upon it are not balanced. If the net force leaves something uncancelled, acting on the object in one direction, a force acting on the object in a particular direction, with nothing else cancelling it out. To visualize these things, we draw free body diagrams. They are specifically vector diagrams showing only the forces acting on the object. We always show the object as a dot, whether that's a mouse, a house, a cow, a flying squirrel, some kind of airship, marvelous minivan. They're all represented as a dot. Here we'll give you an example with an object that happens to be at rest. It would be this orange book here. We're going to consider the forces acting upon the orange book here. we're going to follow this rule. We show each force acting on the object as a vector, and those vectors radiate from the dot representing the object. So the middle book in this stack will represent as the orange dot to color code it with the orange book. The forces acting upon it, one of them is gravity, pulling the book down. Another is the force of the weight of the book above, pushing it down. And another force is the normal force applied by the blue book below. And that force is pushing up, and we should define normal force. Normal force is the force applied by a surface perpendicular to itself. So when a surface applies a force, it applies a force perpendicular to the surface. And so we consider that force applied by the blue book as being a normal force. It's applying a force upward, which would be perpendicular to the surface of the blue book. By the way, the top book, maybe red or brown, whatever it is applying a force downward, also perpendicular to its surface. We want to show here that we expect this orange book to be at rest. If it's an object at rest, then the forces on it must cancel to zero. And we're showing here that the force upward on the orange book is equal and opposite to the force downward on the book. The forces downward on the book of gravity and the weight from the book above are canceled by the normal force upward from the blue book below. So that gives you a net force of 0 and explains to us why the acceleration would be 0. We'll show this in equation form. Okay, so same vectors, same book, same situation, but now we've labeled the vectors as forces. Here's the force, the normal force by the red book downward, gravity force, gravity pulling down on the orange book, and the normal force of the blue book pushing upward. And that's going to produce a net force, the sum of all those forces. Two ways to represent net force are sigma F, which is the sum of all the forces, and net force, which means the same thing. So we've got the normal force from the blue book upward plus gravity's force downward plus the normal force of the red book downward. And you can see that those would have these signs, right? The blue book's force would be upward, the gravity force is down, and the normal force of the red book is also down. And so actually these two added together are going to be equal and opposite to that blue one. They're going to add up to a net force of 0, which helps explain why the object is not accelerating. It was at rest and remains at rest. Well, that brings us to Newton's second law. Newton's second law says the net force of an object is equal to the mass times the observed acceleration. So if we observe an acceleration, if we can measure that, have the number for it, and multiply it by the mass that's being accelerated, we'll find the net force on it. This is Newton's second law in equation form. It can be rearranged to solve for the acceleration, the observed acceleration, which is the net force divided by the mass. Newton's second law of motion states that the acceleration of an object depends upon two variables. You can see them here. The net force, right there, which is the vector sum of all the forces acting on the object, and the mass of the object here. So you can see that as the net force goes up, the acceleration goes up. As the mass of the object goes up, the acceleration decreases. They're inversely proportional, the mass and the observed acceleration. So where there's more net force on the same mass, the result will be a greater acceleration, right? If the mass stays the same but the net force gets bigger, then this acceleration will increase. Where there's greater mass, that means greater mass down here, but the force is staying the same, then you'll have a smaller acceleration. Alright, this leads us to questions we can ask to help us solve the problems. Is there an observable acceleration? If the answer is yes, then the net force is in the same direction as that observable acceleration. Also, if the answer is yes, then you can calculate the amount of the force acting on the object. You just take the observed acceleration and multiply it by the mass. That gives you the net force that's acting on the object. Vice versa, right? If you know the net force and you know the mass of the object, then you can solve it for the observed acceleration, the amount of it. If the observable acceleration is 0, if there's no observable acceleration, the object is either staying at rest because it was already at rest, or staying in motion in the same direction as it was already going before the problem started. If that's the case, if there's no observable acceleration, then the net force on the object must be 0. So when you add up all the forces, they have to cancel out to 0. All forces must cancel to 0. This will help us solve our problems. Okay. Newton's third law is that for every action force there's an equal and opposite reaction force. Simple equation here. Action force equals the negative of the reaction force, because negative tells us the direction. Here's an application. If Fox is pushing on the wall is pushing back on the Fox with the same amount of force. We'll just show that with free body diagram. This is representing the Fox, this is representing the wall. The Fox has experienced the same amount of force from the wall as the wall is experiencing from the Fox. If the Earth is pulling on a satellite, the satellite is pulling on the Earth with the same amount of force. We'll just consider the Earth down here and the satellite. The Earth is experiencing the same amount of force of pull from the satellite as the satellite is feeling for a force of pull from the Earth. They're equal and opposite action and reaction forces. If a truck is pushing the road backward, the road is pushing the truck forward with the same amount of force. Here's your truck on the road. The truck is, well, first of all, the force of the truck is on the road, pushing the road backwards, right? That's an action force. Meanwhile, the truck is feeling a force forward from the road because of, in reaction to the force the truck put on the road. So these are action and reaction forces. They're equal amounts and opposite directions. Finally, this is a more complicated example. If the tension of a crane's cable, like this cable right here, cancels some of the force of gravity on a load at rest on the ground, sorry for the double on there, then the normal force applied by the ground on the load will be lessened by that amount. So let's see the free body diagram make sense of all this. So you have this load that is partly resting on the ground, but it's being pulled up by a cable with a certain amount of force, not enough force to accelerate the load upwards. But so here's the force of gravity on the load downward, gravity pulling it down. Here's the force of the pull of the cable, the tension applied by the cable. And the ground must supply the extra force so that the total forces upward cancel the total forces downward, or the force of gravity plus the force of the cable plus the normal force all equal out to zero. That leaves the box still at rest but not pressing as hard on the ground. Therefore, the ground, the force that it feels, the normal force it feels from the box resting against it, pressing against it, is less than it would have been if the cable hadn't been pulling on the box. If the cable hadn't been pulling on the box, well, see, these two are equal and opposite, right? This blue force representing the force of the box on the ground is equal and opposite to this green force representing the ground's force pushing up on the load. But notice that if the cable was removed, the normal force of the applied by the ground on the box would have to be a lot bigger. If you thought of this box as sitting on a scale instead of the ground, then the scale's reading would decrease as the cable bore more and more of the weight. As the cable cancels more and more of gravity's force downward on the box, then the scale reading is going to be less and less, right? Okay, as an overview then, we have the central role of acceleration. We said Newton's laws have to do with the relationship between forces and acceleration, and here we see that Newton's second law, which is force equals mass times the observed acceleration, that involves acceleration. And over here from our kinematics, you know, we've already seen a bunch of equations that we can use to calculate acceleration, knowing initial velocity, final velocity, displacement, and time. And so acceleration is our bridge between these two things. So we will have to go back and forth between Newton's laws and kinematics. We're never going to escape our kinematics. Still got to know them. Don't forget that this net force over here is just the sum of all the forces acting on the object. So they might be positives or negatives, but you have to add them all up to get your net force.